Oh, frabjeste collude calais. That's a phrase of the Mad Hatter from Lewis Carroll's childhood story tale, Alice in Wonderland. And I'm quite excited today because after that little venture I did where I described many representations of the imaginary numbers under multiplication, we're going to use how we can partition it into 4 different classes to help evaluate this, in my opinion, kind of beautiful or neat problem. So the problem tells us to find the ratio of the finite sum of all the imaginary powers of I from 1 to 2019 over the finite product of all the imaginary numbers from I of k equals to 1 to 2019. So to write this out, this would be like I plus I squared plus I cubed plus dot 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 plus, and then I go up to I to the 2018 plus I to the 2019. And here on the other hand, I have I times I squared times I cubed times, and now I'm going to leave these terms out intentionally. Remember, this is important. I to 2016 times I to 2017 times I to 2018, and then times I to 2019. And just as a quick aside, the reason why we use the letters sigma and pi to denote sum and product is because sigma is the Greek equivalent of the letter S. I'm probably not pronouncing it properly, and pi, correctly pronounced P in Greek, is the Greek analog of P, which is why we use these giant notations. So, how are we going to solve this? Well, let's go and handle with the numerator first. Numerator seems kind of easy. We have terms being added that are just off by a factor of I. See here, like a factor of I here. I times I equals I squared, etc. So what does that mean? That essentially means what we have here is a geometric sequence. And if we have a geometric sequence and we want to add its terms up, we can immediately pull out the finite geometric series formula, which is the following. Sn, where n is the highest index you raise to, equals the first term of the geometric sequence times 1 minus the common ratio raised to that index over 1 minus r. There's an equivalent way you can write it as well, but I prefer this way. So let's go and calculate it right away. The first term is I. The common ratio is I, so this is I, and we have 2019 terms, so up to 2019. And then 1 minus I. And now here we'll pull a trick using the partitioning of 4, because essentially, well, we're not going to go and like multiply I all those many times and go through those rotations. No, let's be smart about it. Basically, what's the closest number? 2019, that's a multiple of 4. And then from there, we can narrow down which equivalence class this guy belongs to. Well, that turns out to be, which will become of great importance later on, this guy, 2016. And how do I know that 2016 at the top of my head is divisible by 4? Well, it's because that 2016 is even, because it has 6 over here as a digit. And also, I see that it also consists of these digits 20 and 16, which are themselves multiple of 4. 4 times 5 equals 20. 4 times 4 equals 16. There's probably some other heuristic trick to check for divisibility. Really, there's quite a lot. So you can try your own. To be honest, I only realized this after I cheated and did it at the calculator. But I mean, that's the great thing about like mathematics. We don't have to think like cold, unfeeling machines. No, we can go beyond that and get some help. Although we do have to, there's kind of a love and hate relationship in there along the way. But yes, 2016 is divisible by 4. So that means if we count up the remaining congruence classes that come after, this is 1, this is 2, this is 3, this is the third element in Z4, which would correspond to I to the 4k plus 3, which means I to the 2019 must be negative I. So we have I times 1 minus I over 1 minus I, which is I times 1 plus I over 1 minus I. Okay, I'm going to leave this here for now, although what you would usually like to do conventionally is we don't like imaginary numbers in the denominator, so we would multiply this by 1, the conjugate of 1 minus I, which is 1 plus I, and then simplify. But I'm just going to go and compute the product in the denominator right away first. And yeah, obviously, so this is where it works very beautifully with these guys. Like, it's going to be just obviously a pain to just go and like, oh, this is I, this is negative 1, this is negative I, and then compute that all those like individually. But here's the trick. Now that we know that we have a list of i's from 1 to 2016, we can basically find what divides 4 into 2016. Basically 4 times what equals 2016. And that will count the number of these equivalence classes that we have. Then simply multiply it by the corresponding equivalence classes of these guys, and then we're done. We get the finite product. It's quite amazing. So here we need the calculator. So what is 2016 divided by 4? 2016 equals 504. 504 times 4. And you can check this using long division algorithm like so, if you want, but I'm not going to bother. So there's going to be 504, we count, I repeat again, 504 of these i's, 504 of these negative 1s, 504 of these negative i's, and 504 of these 1s, period. And then we have I to 2017, which is then I, negative 1, and then negative I. So this product over here, I'll just call it Pn. This is S of 2019, then I'm going to call the product P of 2019. This is simply, since we have 504 and multiplication is commutative, this is just 504 raised to the 4 power. I multiply it by I, by negative 1, and by negative I. We don't care about the 1 since that just gives us the same thing. Then we multiply by these guys again. So I get an I, and a negative 1, and a negative I. So then multiplying it, I get 504 to the 4, and now I can simplify these guys. This is just these guys squared, so I times I squared equals negative 1, negative 1 times negative 1 equals 1, negative I times negative I, that's positive I squared, so that's negative 1, so I just end up with a positive 504 to the 4th power. Okay, and now, yep, I guess I'll need to simplify this by the conjugate now to make things easy. So S of 2, pardon, this pen is getting very dull. S of 2019 equals I times 1 plus I times 1 minus I, 1 plus I, 1 plus I. And then now I have to do this stupid FOIL, which I might make mistakes. Please correct me in my work if I make mistakes. Everyone makes mistakes. That's what makes us human. The beauty of it all. Plus 2I plus I squared. And then this is just a difference of 2 squares. So then I just get 1 minus I squared, which is really just 2, because 1 minus I squared equals just 1 minus 1, which is just 1 plus 1, which is 2. And now I multiply the I here, so I get I It's 2i squared plus I cubed over 2. So I cubed becomes negative I. So I just get I minus I. That cancels out. Yay, we love when things cancel out. 2 to the negative 1 divided by 2. Yep, very beautifully, that becomes negative 1. And so our answer, and we are done, baby! Oh, pardon. Is that this thing, I'll just call it S 2019 over P 2019, sum over product from 2019, is just negative 1 over 504. Yes. Yeah, so we get basically a negative rational number that's very, 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 very close to 0. Essentially, we take this. Again, like with most things in mathematics, we really don't care about the answer. It's really about the journey on what takes us there. And we've really combined a whole bunch of things together, which in this case I hope that you appreciate why it was important to go and partition I into parts of 4, and just an application of finite product and a geometric series formula. So I hope you enjoyed the video. Until then, have a pleasant day.